So we'll continue the discussion on organic chemistry for the remaining of the semester. Organic chemistry is a topic where we strictly focus on the study of carbon compound. So I think until 1800, there's no clear differentiation between organic chemistry and inorganic chemistry. You will probably heard about a Swedish chemist called Torbjörn Bergman in the 1770s. He thinks the difference between the material or the compound we obtain from living organism, the reason why it's different than the mineral is that it contains the vital source. Okay, so this is because a lot of organic organism is based on carbon, and that's why nowadays we call that organic. Until later, someone figured out you can isolate soap from fat through basic hydrolysis of fatty acid, and then by changing the pH, he was able to isolate fatty acid with different melting point, and that is when people start accepting the concept that there are a study called organic chemistry. Okay, so a lot of, including all the coordination compound, you recognize that their ligand has carbon in it. Okay, so in organic chemistry, we'll be dealing with these elements that is bonded to carbon. So you can see all the halogen, and the electronegativity is extremely important in this regard because that will control the reactivity of your compound. Okay, so let's have a brief story on this very complicated molecule, vitamin B. It has 63 carbon and 1 cobalt center. You can still call it a coordination compound, but the discovery of the synthesis of vitamin B is really established the fact that we can basically make anything we want as long as you have the correct structures. Okay, so this is a water-soluble vitamin. So by looking at the structure, if you already learned organic chemistry, you should be able to recognize these amide group are extremely polar. Remember the definition for being polar? Okay, that means if the electron clouds are polarized and is capable of forming hydrogen bonding with water. So when there's a lot of water molecules surrounding this compound, it becomes water soluble. And it's a coordination compound with these amine donating the electron to this cobalt center. And this is the essential cofactor that's involved in the metabolism of a lot of pathway. Okay, so if you do not have vitamin B12 in your system, you're likely to get sick. There will be a lot of different kind of disease. You can go on Wikipedia and read about it. Okay, and then so generally there are certain type of bacteria that's capable of producing vitamin B12, and then the cattle, sheep or cow eat the plants, and then they will have some amount of vitamin B in their meat. Okay, and then we consume those meat, we get those vitamin. And in the study of vitamin B, not just the synthesis of it, but more on its biological and medical aspect of it, has resulted in 5 Nobel Prize in 1900s. Okay, so in the industrial production of vitamin B is really reliant on fermentation. So I think some of you will go into the biotechnology in the future. That's where you can engineer the metabolism or metabolic pathway of various microorganisms and force these microorganisms to produce the compound that you want. Okay, so sometimes it's more efficient than making it in lab. Okay, but knowing how to make it, it's just a capability that you can acquire, that you can develop over time. So organic chemists are very ambitious in terms of trying to produce what the nature do. For those who are interested, I have a book that's called A Molecule That Changed the World. So you guys feel free to flip it after class. Okay, so this is synthetically feasible in 70 steps. Okay, so when we are talking about multi-step synthesis, we have to think about yield. So theoretically, it is the ratio of actual amount versus your theoretical amount. So assuming each step is 90%, after 2 steps you're at 80%, 3 steps 70%, okay? Assuming each step is 90%. So when you're going through a lot of steps, then your final overall yield would be very low. So if you think about in TSMC, when they have these multi-layer devices, their yield has to be very high. It has to be over 99.999 so that after multiple steps, they still have a good product. Okay, so this is what it looked like. There's several models that you guys will encounter to simplify a complicated molecule. You can actually use a stick model. So we omit all these balls or these atoms that account for where the electrons are probably located. You can get, this is the beautiful structure of vitamin B12. Okay, and I forgot to mention the R group, which is coordinated to the cobalt center. There's various type of the R group, okay, and they have different kind of biological property. Okay, so it took about 100 people and complete the synthesis of this compound. For organic chemists, they basically recognize the functional group and they figured out what we call retrosynthesis. So how can we get there? Okay, it takes years of training to be able to develop that sense of how to make a certain compound. So basically, this compound will be cut up into different subparts. So we can just say a group of students will be focused on figuring out a way to synthesize this. Another group will figure out a way to synthesize this. And not to mention, there's also stereo center. It's located here, and that is also important to the final property. And we'll get to there in a little bit. Okay, so in the end, once all these fragments are made, then you have to figure out a way to put these fragments together. So by knowing the reactivity and the selectivity of your reaction condition that you chose, you can end up with this very complicated molecule. Okay, so over 100 people work on this, and there's a couple key players in this. So the credit has been given to Woodward, who received Nobel Prize in 1965 for his contribution to organic chemistry. So for those of you who were dedicated your study to organic chemistry in graduate school, that's someone you probably should read about his bio, and there are many articles about him. So in fact, many scientists are related to him to some degree, okay? So he has many students in the field of organic chemistry. So remember Professor Craney handed out this handout sheet by Ronald Hoffman, How to Learn, right? So basically Woodward shared Nobel Prize with Hoffman because he devised a rule called Woodman-Hoffman rule that would describe the chemical reactivity. Okay, so he focused on complex natural product and utilized various techniques to confirm the final structure. Okay, so the second guy, the Esther Moser, he basically pioneered this study in Switzerland, and after he was able to accomplish the synthesis of vitamin B12, he focused on origin of life type of research. So it is actually, in fact, a chemical subfield that focused on figuring out the fundamental chemical reaction that may explain how life is created. So we know we're a product of our RNA and DNA, right? So how does these sugar molecule or these base pair assemble together? That is a subfield that some people are interested in. How are these peptide bonds, how are these amide bonds are formed, how are these sugar are bonded together? And another person that worth mentioning is this Dorothy Hodgkin. So she was awarded Nobel Prize in 1964 for her work in X-ray crystallography. So I think you guys are all familiar with the double twin structure or double helix structure of DNA, right? And then it was based on one X-ray crystallography. Okay, you can use X-ray to look at the crystal structure. So she helped out a lot of organic chemists. Once you generate your compound and you make a crystal of it, okay, that means they're very ordered, and then you can shine X-ray on it, and the scattering profile, and you use very complicated mathematical formula, you can figure out its structure. Okay, so let's review different functional group. So if you have your book, let's go to the page 655. Okay, so in the last lecture, we talked about various type of structure. And I think we mentioned all of it in the last lecture. Okay, now just take a minute. Now look through their functional group and compound type. Before we move on, you should be familiar with these terms. Okay, so this is the language of organic chemistry. So you may feel like it's overwhelming or it's a lot of memorization, but actually I think in organic chemistry, besides practicing your nomenclature and practicing your reaction mechanism, eventually it will become part of you. So you don't really have to memorize it, okay? It's just something that you just know. So I would encourage you to either make flashcards for these functional group and then put the name on the back of the flashcard so you can try to remember these things. You know, single bond is alkane, and then get to alkene where there's double bond. For triple bond is alkyne. And then you get alcohol, various type of halogen. So we have fluoro group, chloro group, bromo, and the iodo group. Then there's aldehyde and the various degree of oxidation. Okay, so if you oxidize alcohol, that gives you aldehyde. Then if you further the aldehyde, it will become carboxylic acid. So that kind of explains why when we do a fermentation of sugar, these microorganisms will first produce alcohol, but they also have certain oxidative pathway that will convert these alcohol into acetic acid. It explains why the organic compound can become another compound given a certain condition. Then if you react alcohol with carboxylic acid, you will get ester. And if you react carboxylic acid with amine, you will get amide. And then also there's a triple bond CN, which is called nitrile. So with these special functional group, now look at on the right side of your book, they have their common name, right? So that's something also you need to know for a chemistry major. So it's just how we name these things. So let's flip to page 667. There's a sample problem, and then it basically circle out these functional group. So when we were talking about a very complicated molecule, we first by recognizing its key functional group, right? So that is the key for you guys to starting to recognize the potential pathway that you can synthesize these things. Let's get to the naming of various types of alkanes. I mean, I don't think people actually talk about these very large long chain carbon. Normally you would deal with carbon 1 through maybe 20 on this table. So normal alkane, last time we talked about structure. So for alkane, it has a CN, H2N plus 2, right? When we have an alkene, okay, where you form a double bond, you have to lose 2 hydrogen, so it becomes H2N. So if you have a cyclic compound, okay, cyclic alkane, it will also be the same because you have to lose 2 hydrogen for the carbon to form that bond. Okay, then for the alkyne, it will be 2M minus 2. Okay, you have to take away 2 more hydrogen so you can form that triple bond. Okay, so let's go through the common prefix for various alkane. So that is something you have to know eventually. So you go from methane, ethane, propane, butane, and we know these 4 are gas, right? So the length, the molecular weight, it has some relationship to the physical property of your chemical compound. Okay, then you get to pentane. Pentane will be a very volatile solvent. That's chapter 13 we talk about. So pentane, then we get to hexane and heptane, octane. Oct means 8, and nonane, that's 9, and decane. Okay, and then I know these are somehow harder to remember. For the first time, it's what you will encounter a lot. And usually, when you actually use hexane in lab, you will see a S. So why is that? Okay, so we will think of if we just draw out the structure, we will think this is what hexane look like, right? So this is what we will refer it as N-hexane. This is a linear hexane. But this compound can have many constitutional isomers. That means they're made of with the same amount of atoms, but the way they're connected are different. Okay, so we could move this methyl group in exchange with a hydrogen on here and give you such structure. And we can also move this methyl group to here. Okay, they're all hexane of some kind, okay? And that's why, because they are very difficult to separate by distillation, okay? And that's why when you get this thing, it's called hexanes, okay? So you have to recognize there could be many isomers out there. Okay, so how will we name a branch structure like this? So there's a couple rules in terms of naming. Let's look at this one. So the first rule is say count the longest continuous chain of carbon. So in this case, the longest one is 5. Okay, so for these example, okay, so this one 6, there's no questions, right? And for this one, the maximum amount of number is 5. And for this one, maximum number is 4. Then you go with, that is your parent name for your compound. When we name this compound, that we will call this something something 5. We go back to that table. 5 will be pentane, okay? And then you have these various groups attached to it, and then we'll label the number, okay? So we go from 1, 2, 3, right? So we call that 2-methyl and 3-methyl, okay? Then we condense it. Then that's why we call it 2,3-dimethyl. So if you have more substituent, you will call that di, tri, tetra, penta, hexa, hepta. Then you can recognize these names. The only difference is up here, but the later one would be very similar to what you observe for naming alkanes. So let's do a little practice here. Here it's simple, right? We know the longest chain will be 5, right? So pentane. So we will call that 2-methylpentane, okay? This one, the longest one is butane. So we call that 2,3-dimethylbutane, okay? And then of course there's a much more complicated one. Sometime when you are naming it, you can also count it from here. So 1, 2, 3, 4, 5, okay? So you can say this is a 3,4-dimethylpentane. But according to the IUPAC rule, who control how can you communicate in the same language, we will want the number to be as low as possible. Then you may wonder what happened when I have a very complex side chain. And then that is when things get a little bit more complicated because we will give, sometimes people will use common name for it. So let's look at this branch side chain. Okay, so the longest chain is the C10 carbon chain. Okay, so we call that decane. But for the side chain at the 5th carbon, then we relabel it. So we first describe, this is a propyl group, 3 carbon, right? And that actual branch side at the 1st carbon. So we call that 1-methylpropyl. But its actual common name will be secondary butyl group. So also when we're naming it, if you have methyl, ethyl, we will go with the alphabetic order. Okay, so for that molecule, you can call this 4 and 5, but since we have a rule saying that we should go with the lower number, so we will count it as 3 and 4. For the substituent, we will order it alphabetically. So when we have these heteroatom, okay, these substituent, you simply do the same thing. For example, the one on the left, we call 1-chlorobutane. But a lot of time, because organic chemistry has been around for so long, and sometimes people will use its old name, you will also see butyl chloride. Okay, and you probably recognize this from butyl, is when we talk about these things, we were adding this, we call methyl, ethyl, butyl, right, propyl. Okay, so for the one on the bottom, we recognize the longest carbon will be propane, right? So in this case, because bromo is important, right? So we started with 1, 2, 3, instead of naming it with 3 bromo. But if you follow the rule, you should be able to picture the compound when you see the name. Its old name is isobutyl bromide. There are many examples out there, so once you get to organic chemistry, you will learn more about it, okay? And for the nitro group, then you go with which one is more important. Then you will put it in the right places. Okay, so we briefly talk about isomers because I feel like it's a good example for learning about naming. It's about recognizing the patterns. Okay, let's look at page 642. Okay, so these are other isomers for C4, which is 4 carbon, and C5, pentane. Okay, so there's an isomer. And the common name, as I mentioned before, okay? And also the structure will have a dramatic effect on its density as well as boiling point. Okay, so look at this table and try to see if you can find a pattern. So recognizing when there is branching, generally you lower your boiling point. Okay, that means you have less interaction among themselves, weaker intramolecular forces, so that the boiling point is easier to vaporize these compounds. And also recognizing its density. The density becomes lower when they're branched. Okay, so these are the constitutional isomer. Okay, so that means constitutional is what it consists of. Okay, so they have the same type of atom and same amount of atoms. Okay, and the next type is the stereoisomer. And this will play a big part in organic chemistry. And we'll get to it in a little bit. For having a stereoisomer, you must have a stereocenter. And what is a stereocenter? It's also known as a chiral center. So the definition is a carbon that is bonded to 4 different groups. It has to be 4, okay? It can't be 3. If you have 3, then it's not a chiral compound. Okay, so then if you look at the figure 15.8, okay, this is the analogy to a chiral center. So my left hand and right hand, they're a mirror image to each other. I cannot overlap them completely, but imagine there's a mirror here. I can create a mirror image. So my palm would be similar to what we call a chiral center. That makes sense? It's a mirror image to each other. So if you look at the figure 15.9, you should be able to see 2 types of chiral isomer. Again, they're a mirror image to each other, but then they're different, okay? And now I want to point your attention to the next page and start reading the role of optical isomerism and isomerism in organism and medicines. So the chiral center play a very big part in organic chemistry, as you already read. So some would have good biological property, some will have very bad biological activity. Okay, it's because our enzyme has evolved over the years, only process certain kind of substrate. So one great example is sugar. So there are these what we call the fake sugar. There are many kinds. These sweeteners, they taste sweet, but if you can pick the kind that your body cannot metabolize, then your body cannot gain energy. So that extra energy will not become fat in the end. And of course, in a lot of pharmaceuticals, a lot of drugs, okay, as you read in this paragraph, some of them can be used as a medicine and some of them have very, very bad effect. Okay, there's side effect. And so in organic chemistry, there is a subfield that is dedicated to control the stereochemistry of these compounds. And imagine it's a compound with 10, 20 carbon, and you have multiple chiral center. The ability to control the purity of your final product will be very important because the separation of chiral compounds are generally difficult. Although it's possible to isolate them by special purification technique, but generally if you can get to a very high purity by designing the synthetic route, then you will save yourself a lot of trouble. Okay, so I didn't change the text box here, but let's look at the next page, 645. So there is table 15.4, right? So that is just what we call the cis and trans. Okay, so how do you remember that? When I think about trans, you can think of a chair configuration, okay? And then for cis, you can think of like a boat. So when the things are on the same side, it's called cis. When your substituents are on the opposite side, it's called trans. And sometimes you will also see when the substituents are on the same side, it will be the Z form. And then when they're on the opposite side, it's on the E form. That's just for the simplicity when you have multiple alkene. Okay, so sometimes you will get compound will have multiple double bonds adjacent to each other. And then you will use that E and Z to details. And there are some chemical transformation that you can do to switch it from the cis form to trans form. So for example, the guys that share Nobel Prize with Fraser Stoddard, who came visit us last year, his contribution is to utilize cis-trans isomerization to control these molecular rotor. Okay, so you can think of you have two paddles, and whether it's in cis or trans form, and you can change that by temperature or shining light on it to induce change. So now let's talk about a few syntheses. Okay, so in organic chemistry, you will be given a problem like this on your exam. Okay, so this is to test your ability to recognize the functional group and think about what kind of chemical transformation that you can do to the compound to change its structure. So in this case, this is a variation where the bromination reaction that we talked about in the last lecture, right? You can do a selective bromination of your alkyne to generate this dibromo alkene, and then follow chlorination by adding two chloro group to here. Then you can finally get this compound from the dibromo. And then there you can develop various ways. I mean, there's multiple ways that you can get to your final compound. How can you pick a easiest and the cheapest way is always the pursuit that really tests your ability to come up with a more efficient processes. Okay, in the first step, the reason why I bring up this problem, now we're going to talk about different general chemical reactivity that you will encounter in organic chemistry. So sodium amide is a very, very strong base. If we know ammonia, it can pick up a proton to become a ammonium, right? So this ammonium is weakly acidic, right? So it can give off a hydrogen to a more strongly basic compound. So when we remove one hydrogen from the ammonia, okay, we know ammonia is already base, right? So if you remove that hydrogen, it will want to get that hydrogen back. So we know what is a base. So you can use multiple concepts, right? The ones that will want to take up a proton, or the one that will want to donate electron away to other atom. Okay, so sodium amide is negative charge, and its counter ion is a sodium ion. Okay, so this very strong base can react with this dibromobutane. Okay, so I'm going to draw out the reaction mechanism. So a lot of time in organic chemistry, you would not draw the hydrogen atom for clarity, okay? Since this is so basic, and you can also think about delta G. So in such process, your delta G is less than 0. It will want to pick up the proton, okay, and generate ammonia, okay? Then you get to this transition state. When you pick up the proton, that extra electron on this bond come to this carbon. So you have these extra electrons, and this now become negative charge. And then this electron move down here, let it to form a new bond while kicking away this bromo group. So you end up with, okay, and then you're going to do this again and kick away that bromo group, and then you end up with this alkyne. And recognizing this is a straight line. Why is that? Because alkyne is a sp hybridization. When we have sp3, it's tetrahedral. When we have sp2, it's triagonal. If you have hydrogen here, they are triagonal. Okay, when you have sp type hybridization, it's linear, and that's why I force it to go back to its linear orientation. And for here, when you do bromination, this becomes sp2 carbon again, and then it eventually becomes tetrahedral. Okay, so for this reaction mechanism, if we look at the bromo group, so previously, let's start with this reaction. Okay, so in the presence of a strong acid, whether it's HI, HBr, okay, they all do the same thing. That extra electrons here, this very rich electron cloud, will pick up a proton and generate an intermediate species, and this becomes positive over here because you don't have anything here to balance that charge, and that chloride will come in, and then you end up with your strong acid add across your double bond. When we have a chlorine, you can also do the same thing. Even though it may seem confusing, but still, the electrons are just moving around. When there's an electron going to one side, it can become partially negative, partially positive, and it will attack that chlorine, okay? In this case, it's a bromine here, and then so you can brominate that triple bond and form this double bond. And of course, if you have a lot of these bromine, if you have an extra bromine, it will continue to react with this double bond, and you won't get your final product. So this covers 3 types of reaction that you can do with organic compound. And let's look at more of it, okay? So again, we already saw that. We talked about reaction with a strong acid, where it add across a double bond. But again, here is a selectivity problem that you will learn about later on, okay? How do you control the addition of HBr across a double bond? And why the bromine will locate it on one side and not on the other side, okay? So there's a lot of pattern in organic chemistry, okay? So your reaction condition will dictate the selectivity or where does this extra electron will go. We won't go in there because it's a bit complicated. And then in the last Friday, we talked about where you treat the haloalkane compound with a very sterically hindered base. Okay, this is a very bulky group. You have to, because there's extra hydrogen around it, it's going to undergo elimination reaction. So basically, you will pick up a proton or a hydrogen that is located here, right? And then once you have that negative charge there, it's going to hop back in and kick out this bromide. Okay, you end up with this alkene. All right, then this is a typical reaction that you can do with ozone. Okay, in the presence of ozone, you can undergo oxidation here, and that will generate this ketone compound here. And of course, on the other side, you will end up with aldehyde. And recognizing this aldehyde have very low boiling point, so generally it can be evaporated. So in organic chemistry, it may not seem as simple as what is written down, because in a practical organic chemistry lab, if you look at that structure, that compound is likely to be volatile. Why? Because we mentioned when your carbon is below 5 carbon, generally they have low boiling point. Okay, so if you have high vapor pressure, when you're evaporating your acetaldehyde, you might also evaporate away your methyl ethyl ketone. Okay, let's look at a different step. Okay, so again, it's just a transformation functional group. So going from chloral to this triple bond. So first, we can generate that double bond, right? And add bromo group across that double bond. Does that look familiar, right? That looks just like our first example, right? But we do a different reaction. We do it twice, the elimination reaction twice. We get the alkyne. Then, okay, we already saw HBr. And then here, there's also what's so-called the substitution reaction. And here we have a cyanide. Cyanide is a nucleophile. It has extra electron and is ready to attack another compound. So a lot of base are nucleophile, okay? So the cyanide will come in, okay, so in this reaction, there are 2 pathways. One is substitution reaction, and one is elimination reaction. So it's very common that you will get both mechanisms going on, but if we don't care about yield, okay, it's possible that you can make this compound. So for a compound like this, an example how the Challenger principle can come into play when we're doing substitution reaction. Okay, so there is a bromo. This reaction typically uses acetone as a solvent, and then we know the solubility of sodium bromide is worse than sodium iodide. Okay, so this nucleophile, this iodide, can potentially react, can attack the carbon at this position and generate iodopentane. Okay, and then since sodium bromide is not very soluble, it will tend to precipitate out. So it actually drives this chemical reaction toward the product side continuously until you ran out of the starting material. And the Gibbs free energy also come into play. We think about, then again, in entropy in such system. It's a thermodynamic feasible process, and you use a little trick by playing with the different solid solubility. This will also work if it's a chloro group. Then once you have iodo group, the chemical reactivity is definitely be different than the bromo group. Okay? So we'll start with a practice problem. So let's look at our sample problem 15.3 on page 655. Okay, so in basic organic chemistry, three concepts will occur over and over and over. One being elimination, as you've seen before, okay, where a base come in, pick up a proton, you move the electron around, and then you generate alkene or alkyne. And the second one being addition, where you will add HBr or bromine across the double bond or triple bond. Okay, and the third reaction being substitution. So spend a few minutes, look through this problem, and try to observe the difference in the products and reactants functional group. And then if you already finished reading about it, let's look at the follow-up problems. I think this is the most important takeaway from this chapter, is trying to start learning how to recognize the patterns in these processes. Okay, so the first one, ethyl bromide with hydroxide. NaOH is associated into hydroxide. This extra electron, negative charge, it come in and kick out the bromo group, and that gives you ethanol as what we observe. And that byproduct will be sodium bromide. That is pretty straightforward, right? A substitution reaction. Okay, so let's look at the second one, the hydrolysis reaction. Okay, so we recognize the product. The difference is these two functional groups, right? And you end up with carboxylic acid and alcohol. So it's a very common reaction that you encounter, which is the hydrolysis of an ester. Okay, so how does this process happen? Okay, so it can either go through an acid catalyzed route or a base catalyzed route. Okay, but we won't go in too much details because it's not about writing down the reaction mechanism, but that's something you will have to know in your first semester or second semester organic chemistry in your sophomore year. Okay, so we recognize that the ester becoming acid, right? So obviously it's a substitution reaction that you're replacing this OCH3 with OH. Okay, so this is a substitution reaction. Then the next one is a little bit trickier. Indicate this is acid catalyzed. So you end up with that final diol at the end. That this diol is called an acetal. Okay, so actually the water come in and then one oxygen form a bond with this carbon, right? Gonna give you this. This oxygen is still here, but it just sharing that hydrogen with this water molecule. So this will be an addition reaction. I think That's all for various type of reactions, and you can read more about it in this textbook. And of course, organic textbook will be more advanced. And now I want to discuss a little bit more about different kind of bonding and acidity. So remember, we're talking about acid and base, but because we didn't talk about organic chemistry first, we said we'll talk about the effect of substituent near the end of the semester. So let's look at a hydrogen model, a dihydrogen. So you guys remember seeing an energy plot for dihydrogen. So from quantum mechanics, we know there's an energy well, look like this, from the first semester. Okay, so this is the distance between these two hydrogen. Okay, it will be at its lowest energy when the bond length is at 74 picometer. Okay, so when they go to over here, when they're too far apart, there's no energy. When they're too close, because there's some repulsion between these atoms, between the electron cloud, if you want to force them very close, you will have to put in a lot of energy. So the same picture can be applied to carbon-carbon bond. Okay, so we previously have a number of 78 picometer. So if you think about chemical bonding, the atom has its nucleus, right? So neutron and proton all pack up in that very dense nucleus. And then you have these electrons just flying around the nucleus. When a covalent bond form, okay, they have to approach each other. When we say a covalent bond form, that means their orbital overlap, and they're sharing the electrons. You can find these electrons within their joint orbitals. Okay, so most of the atoms that we're dealing with, their electron cloud, is between 100 to 300 picometer. Okay, that's just the old unit that people use. Okay, and what is 100 piconewton? That would be equal to 1 angstrom. So you will see this unit in describing a lot of chemical bonding. And at the time this concept developed, there's no such thing called nanometer, okay? This was invented later. So what you have to remember is 1 nanometer, this is 10 to the negative 9, right? Equal to 10 angstrom. Okay, so this gives you an easier picture to remember what is an angstrom. 1/10 of 1 nanometer is angstrom. Of course, you can do the unit conversion and you can get to pico. Okay, so why do I mention this? This is for hydrogen. For a dihydrogen molecule, its bond length is 78 picometer. It's talking about the overlapping region of their orbitals. So what about carbon? For carbon-carbon bond, single bond, this value will be 154 picometer. So that is also 1.54 angstrom. Okay, so what about double bond? They're a little bit closer. This bond becomes a little bit stronger. It becomes 134 picometer. And for an alkyne, a triple bond, they become closer and closer. Okay, so that has to do with the increase in their overlap orbital. And they have to be closer, otherwise they might fall apart. Okay, so this is just to put in perspective of their bond length. You can also think of it as angstrom. You will see this over and over. Because when we are dealing with polymer, okay, we know each bond, polymer are a lot of these carbon chain connected together. These repeating units connect together. How long is a polymer chain? Okay, then it gets into how the molecule is oriented. Is it oriented like this, or you have a kink like this? Their overall length will be different. Okay. And of course, after talking about bond length, we will talk about bond energy. Let's look at what we call the bound dissociation energy. So go back to the example of the CC bond, okay? So when my substituent is the hydrogen, the bond dissociation energy is 90 kilocal per mole, okay? The amount of energy required to break this bond. This is how strong this bond is. When I have a benzene ring next to it, to break this bond, it's an even higher energy. Well, if I have a phenyl ring, to break that, it's even higher. okay? And for acetone, okay, if you want to break the CH3 off the acetone, however, it's lower. So why is that? So it has to do with the electronic structure of the molecule, and that's why organic compound, they have a very diversified reactivity. And let's look at a very extreme where you have a lot of steric hindrance. For example, you have a molecule similar to this, but instead we are just taking this a step further. You can think of this carbon as this carbon, but you're just replacing hydrogen with a benzene ring where we have a hexaphenyl-ethane. So if you think about a benzene ring, I mean, the way I drew it, it's much smaller. It's about the same size as the methane, but in reality, it's much bigger, okay? So when you force all of these substituents onto an ethane, guess what? The bond dissociation energy becomes 8 kilocal per mole, because this is going back to this picture. You have all these substituents, but you also want to maintain that bonding, so that makes this bond very weak. Because accommodate all of these substituents, there's a lot of steric, a lot of repulsion, right? So the bond becomes very weak. All right. Okay, so I think that's it for the bonding. Now we'll get to the acid and base section. Okay, so we know HCl, very strong acid, right? A 0.1 molar HCl that will give you a pH of 1. So its pKa sometimes is regarded to be a negative scale. Okay, that's very strong acid. It will readily dissociate and give off that proton. And for carboxylic acid, for example, for acetic acid, which is obtained by oxidation of ethanol, after 2 oxidation, you get acetic acid. And we know that this is a weak acid. It has a pKa value of 4.7. And of course, for a longer carbon chain, this value may change. Okay, remember the calculation we done in the acid-base chapter? So for alcohol, so we talk about acid-base chemistry. For ethanol, what will be the pKa of this? We know in alcohol, this hydrogen, the way the bonding it is for alcohol does not readily dissociate. But when we are talking about acid-base chemistry, in water, it's acting both as an acid or base depending on what substance you're talking about. So in a case where you have a very, very strong base, for example, the sodium amide that you saw before, you can take away this proton because this proton is acidic compared to sodium amide. And then so the pKa of this compound will be about 16. Okay, so in organic chemistry, you will want to think about pKa will be how easy it is to remove that proton, or how easy for a compound to pick up a proton from another compound. So when you have a very large pKa, what does that mean? It means you're very basic. The concepts in general chemistry will keep coming back in organic chemistry. So about this carboxylic acid, what's special about carboxylic acid? It has, once the acid is dissociated, we know a base come in, right? The proton is lost. So that places a negative charge, the acetic acid, okay? So on this carboxylate, you have resonance structure. What is resonance structure? Again, in organic chemistry, we care about electron movement or electron flow. This extra lone pair electron can come here and kick off the bonding that originally was placed here, right? You will see this a lot in organic chemistry that represent resonance structure. So these two structures are just in resonance. The electrons are just hopping around. And we will call that the electron is delocalized. Okay, and what is the substituent effect around the carboxylic acid? So generally, when we have an electron withdrawing group, generally that will stabilize this anion structure because we do not want all the electrons to be concentrated at one location. There is an electron withdrawing group, so how do I know whether it's an electron withdrawing group or not? we have to think about electronegativity, right? Electronegativity will affect the polarizability, means how easy it is to move that electron around, okay? So remember, we recall the concept of electronegativity. When I have a fluoro group, the most acidic version of acetic acid will be a fluorinated acetic acid, okay? I replace all the hydrogen with this fluoro group, the most electronegative element that you could have. Guess what the pKa would be? The pKa would be 0.23. And I can remove the one right now with my table. If you remove 2 fluoro, if I only have 1 fluoro group, that will give me a pKa of 2.59. So what if it's a chloro group? The chloro group is not as electron withdrawing as fluoro group, right? So that would increase the pKa by a little bit. So it becomes less acidic compared to the fluoro. Okay, if we mix these together, to some extent, they could react, right? So because this is slightly more basic, or we think about the conjugated base, because it's not that willing to dissociate, it will immediately pick up a proton from a more acidic compound. So recall this acid-base chemistry to organic chemical reaction that as you saw previously. So as we move down the table, let's say we have an iodo group. Then that pKa becomes 3.12. And we know this is a log scale. Okay, a small difference in pKa that actually change your amount of free proton or the solvated hydronium ion concentration by a lot. Okay, so what if we have an electron donating group? So for example, if we replace this substituent with the CH3 group, so the pKa become 4.87. Okay, you see that huge difference between their pKa. Okay, so generally with the electron withdrawing group, it stabilizes resonance structure, and we know in a Gibbs-free energy equation, if you're at the lower energy state, right, for your final product, you can stabilize that final product, then this is more energetically favorable. So generally, electron donating group will destabilize this carboxylate anion. It becomes a weaker acid. Then similarly, we can observe the same trend in aromatic carboxylate acid. So it could have a benzoic acid, okay? It has a pKa of 4.19. And remember with the CH3, you have a pKa of 4.87. Okay, so just a benzene ring, benzoic acid, it has a pKa of 4.19. If you have an electron donating group, such as a methoxy group, okay, because you have these lone pair on the oxygen, it's donating electron, even more than just a simple methyl group, right? So if you're donating an electron through this aromatic ring, from the previous concept, we know electron withdrawing group will make a weaker acid. In this case, its pKa would increase to 4.46. So let's talk about the example with halogen. With the chloro group, we already saw that in the previous reaction. What will happen with the chloro group? That will give you pKa of 4. So that means you're making it more acidic with a slightly withdrawing group. Okay, and in organic chemistry, the most electron withdrawing group is probably in the nitro group. And cyano group is also regarded as an electron withdrawing group. Think about the electronegativity. So for their pKa, for the cyano group, that will get down to 3.55 and 3.41 for cyano and the nitro substituted benzoic acid. These are the trends that you need to know, and you need to be able to explain why some compound is more acidic than the other. All right, so since we're already talking about acid, we will talk about a few different ways. So this is where inorganic chemistry come back in again, or the redox chemistry come in again. We will actually use a lot of inorganic salt in organic chemistry lab. So the most simple one, this one will be something you guys will do in organic chemistry lab, is the oxidation of toluene in the presence of potassium permanganate. So you see this all the time in the redox chemistry, asks you to balance the charge, right? So this is the oxidant that will give oxygen to this toluene molecule, right? And you end up with carboxylic acid in the end. But however, if you have double bond that is present in your molecule, for example, a simple alkene, this is aromatic double bond, so the reactivity is a little different. But for a simple alkene, let's look at this simple structure. Okay, you have alkyl group on the side. Potassium permanganate will produce, it will basically cleave off at the center. So when you plan a reaction, let's say your substrate has a double bond somewhere down here, then you shouldn't use potassium permanganate to do the reaction because you will break your compound apart. So that's something you have to think about. Okay, and another common one that you guys deal with would be chromium, right? So previously we mentioned these transition metals that have multiple oxidation state. So chromium, although it's very toxic, it is a very common oxidant that is used in making carboxylic acid. So when you have alcohol, I believe it was under acidic condition for this reaction to go forward, you can convert an alcohol into acid. Another one is where you can convert aldehyde to carboxylic acid. It's with silver and in the presence of ammonium hydroxide. And this is also what we call the silver in the mirror experiment, 银镜实验, right? It can detect aldehyde. So in some cases, back in the days, people actually use such process to detect functional group. When this happens, okay, when I see a pH change, oh, then I probably have aldehyde. So these are the common reagent that is seen for carboxylic acid. You can also go backward. That would be reduction. Okay, so the reagent here would be various hydride, but of course there can be borane and the various hydride. Basically, you have this extra pair electron, right? And then that make it nucleophilic that it can attack this carbon. And then from the electronegativity, we know this is partially negative and this is partially positive. So the hydride will react with this carbon and slowly removing all of your oxygen until you're left with just one oxygen. You cannot react further. But there's also ways that you can completely remove that oxygen. So where you can go from alcohol to simple alkane, okay, or alkene. And then we will talk about an example of making a chiral alcohol. So let's start with benzaldehyde. And there are something we call the chiral catalyst. So the catalyst itself has some chirality to it. If we think about a structure look like, so I will omit the other side, okay? It can be a chiral center, right? Because we have a hydrogen here, but depending on where hydrogen is, you can get different chirality, okay? So we can have one bond. This is the way we draw. A bond is pointing up and a bond is pointing down. That means you have a hydrogen that is standing out of the board. But the other bond, your bond that connect here to the oxygen is behind the board. Okay, so for here, the bond that connects to the oxygen is out of the board. Okay, so this chiral catalyst can really control the chirality when you having diethyl zinc. You can form these organometallic compound where you can really, we know zinc is +2, right? So balance that charge, that gives, here are 2 negative. Even though this is the organometallic species, but this will give you a nucleophilic character, right? So then in the presence of this titanium chiral catalyst, titanium can interact with this benzaldehyde, right? And also the chirality will provide a steric hindrance that will control in a similar way that as how enzyme can control the selectivity of your reaction. It can interact by binding coordination between titanium and this aldehyde. It limits how this zinc can come in, or how this zinc organometallic species can come in and attack. And then you can make chiral alcohol. So this is a chiral center, the hydrogen pointing out of the board. So it will give you the difference in their chirality, and then you will get a selectivity. This will be 97%, and this will be 3%, okay? Versus without the catalyst, when you do this reaction, because you don't have a control over its chirality, this reduction reaction will give you 50-50 of the mixture. Okay, so this is one simple example of how we can use different organometallic species that's developed by inorganic chemistry and used to do chemical transformation on organic compounds. I think that's all I have for today. Please go back and read the book, and then we'll have a couple more lectures on organic chemistry.